Modern technology's vulnerability. Critical infrastructure systems across the globe face unprecedented risks from the accelerating magnetic field changes documented throughout 2025. Our electrical power grids depend on stable magnetic conditions because transformers and transmission lines are sensitive to magnetic field fluctuations. When the magnetic field experiences rapid changes, it induces electrical currents in power lines that can overload transformers and cause widespread blackouts. The 1989 geomagnetic storm that knocked out power across Quebec for 9 hours demonstrates how magnetic disturbances can cripple electrical systems. However, magnetic pole reversals occur gradually over thousands of years according to paleomagnetic records, meaning power grids face risks from space weather events like solar storms rather than sudden magnetic field collapse. Satellite networks that provide communication, navigation, and internet services are extremely vulnerable to magnetic field disruption and space weather effects. Satellites operate outside Earth's protective atmosphere where they rely on the magnetic field to deflect harmful radiation from space. As the magnetic field weakens, satellites experience increased radiation exposure that damages their electronic components and shortens their operational lifespans. The GPS satellite constellation has already required more frequent maintenance and replacement due to radiation damage from weakened magnetic protection. NASA research confirms that while magnetic reversals happen gradually, the weakening magnetic field during the transition period increases satellite vulnerability to solar particle events and cosmic radiation. Navigation systems used by aircraft, ships, and ground vehicles all rely on magnetic field measurements for accurate positioning. Airplane autopilot systems, marine compasses, and smartphone navigation apps require precise magnetic declination data to function correctly. As magnetic field changes accelerate, these systems are producing increasingly inaccurate readings that create safety hazards for transportation. Commercial aviation has already implemented new procedures requiring pilots to verify magnetic compass readings against GPS coordinates because magnetic navigation is becoming unreliable. The accelerating magnetic pole drift documented in 2025 means navigation systems require constant recalibration to maintain accuracy. Computer systems and electronic devices face potential failure during severe geomagnetic storms because they're designed to operate within specific electromagnetic parameters. The integrated circuits that power everything from smartphones to industrial control systems are sensitive to electromagnetic interference. Strong magnetic field fluctuations can induce electrical currents in electronic circuits that cause temporary malfunctions or permanent damage to sensitive components. Modern electronics lack the hardening necessary to survive severe electromagnetic effects, though the gradual nature of magnetic reversals provides time for technological adaptation. Banking and financial systems that rely on electronic transactions and digital records would face significant disruption during severe space weather events. Credit card systems, ATM networks, and stock market trading platforms all depend on satellite communications and computer networks that could fail during electromagnetic storms. The global economy operates on electronic transfers and digital record keeping that remain vulnerable to electromagnetic disruption. NOAA and FEMA have established protocols for geomagnetic storm preparedness that include backup systems for critical financial infrastructure. Food distribution systems in developed countries depend on complex logistics networks that coordinate transportation, refrigeration, and inventory management through electronic systems. Trucks delivering food to grocery stores rely on GPS navigation and electronic communication systems to operate efficiently. Refrigeration systems that preserve food during transport and storage require electrical power that could be disrupted by geomagnetic effects on power grids. Modern agriculture uses computerized equipment for planting, harvesting, and processing crops that would face challenges during severe electromagnetic events. Medical systems and hospitals operate life support equipment, diagnostic machines, and pharmaceutical manufacturing that all require stable electrical power and electromagnetic conditions. Patients dependent on electronic medical devices like pacemakers, insulin pumps, and dialysis machines would face serious risks during severe geomagnetic storms. Hospital backup generators and medical equipment aren't designed to handle intense electromagnetic interference. Emergency preparedness protocols now include provisions for protecting critical medical equipment during space weather events. Water treatment and sewage systems in urban areas rely on electric pumps, computerized monitoring, and automated control systems that could fail during electromagnetic disruption. Cities pump water from distant sources using electrical systems and treat sewage through processes that require constant electrical power. Urban populations that depend on these centralized systems would lose access to clean water and sanitation during extended power outages. Emergency management agencies have developed contingency plans for maintaining essential services during infrastructure disruptions. Transportation networks including air traffic control, railroad signaling, and highway management systems all depend on electronic communication and navigation that electromagnetic storms could disrupt. Air travel would face significant challenges without radar systems and electronic navigation aids that keep aircraft safely separated. Rail transportation relies on computerized signaling systems that prevent collisions and coordinate train movements across networks. Highway systems use electronic traffic control and emergency communication systems that remain vulnerable to electromagnetic effects. Manufacturing and industrial processes use computerized control systems, robotic assembly lines, and electronic monitoring that could shut down during severe geomagnetic events. Chemical plants, oil refineries, and nuclear power facilities require constant electronic monitoring and automated safety systems to operate safely. These industrial facilities have implemented backup systems and electromagnetic hardening measures for critical operations. The industrial infrastructure that supports modern civilization has developed resilience measures for space weather events. Government preparations for electromagnetic disruption include established NOAA and FEMA protocols for geomagnetic storm preparedness rather than classified extinction-level threat programs. Military installations have implemented electromagnetic hardening measures for essential communication and defense systems, while civilian infrastructure continues developing protective measures. Emergency management agencies have developed contingency plans for widespread power outages and communication failures based on documented space weather risks. Scientific institutions have studied the cascading failure effects that severe electromagnetic events could create across interconnected technological systems. Computer models show that failure of satellite communications could trigger failures in power grids, which would cause failures in water systems, transportation networks, and financial systems in sequence. The interdependence of modern technological systems means that failure of major components could cause failures throughout infrastructure networks. However, the gradual nature of magnetic reversals provides time for adaptation and system hardening. The mounting evidence of accelerating magnetic field changes, combined with increasing technological dependence, has prompted researchers to examine whether current conditions might indicate approaching critical thresholds. While electromagnetic risks operate through conventional space weather processes rather than catastrophic scenarios, the patterns emerging in 2025 suggest that understanding the timing of these changes has the timeline question. Determining when these planetary changes might reach critical levels requires examining the evidence Thomas compiled and comparing it to current observations. Thomas's original timeline calculations placed significant catastrophic events in Earth's past, though his claims about precise cyclical timing lack scientific foundation. While orbital and solar cycles do affect climate patterns over long periods, no evidence supports regular crustal displacement resets occurring on predictable schedules. Thomas connected his timeline to worldwide flood myths and geological evidence of rapid climate change, suggesting that catastrophic events followed patterns that could be used to predict future occurrences. He calculated that the next catastrophic pole shift would occur sometime in the early 21st century, with his predictions placing the probable time frame between 2000 and 2030. The most likely period, according to his analysis, would be the 2020s, when multiple planetary factors would align to create conditions he believed favorable for crustal displacement. Current observations from 2025 show some alignment with the warning signs Thomas predicted would appear in the decades preceding catastrophic events. He described a period of accelerating magnetic pole movement that would begin approximately 60 years before major events. Magnetic pole tracking data shows that significant acceleration began in the 1990s and has intensified dramatically since 2000. The exponential increase in pole movement speed observed since 2019 corresponds to what Thomas described as the final phase of magnetic instability. Though mainstream geophysics interprets these changes through conventional field evolution rather than precursors to catastrophic displacement. Mathematical models developed by researchers studying planetary risk assessment have created algorithms for evaluating catastrophic timing based on multiple variables including magnetic field behavior, seismic activity patterns, and climate indicators. However, mainstream geological consensus sees no imminent catastrophic displacement, with current meteorology and geophysics predicting normal field evolution rather than rapid breakdown within decades. The models show correlations between various planetary phenomena, but these correlations operate through conventional geological processes rather than the catastrophic mechanisms Thomas proposed. The acceleration rates observed in 2025 have prompted some researchers to examine whether critical threshold conditions might be approached sooner than conventional geological timescales suggest. Magnetic field decline has accelerated in certain regions, while magnetic pole movement shows continued acceleration patterns. If current trends continue, some researchers suggest that significant magnetic field changes could occur within decades rather than the thousands of years typical of geological processes. However, these projections remain within the bounds of normal magnetic field evolution rather than indicators of catastrophic crustal displacement. The convergence of multiple planetary phenomena has created what some researchers describe as a period of increased geological activity worthy of scientific attention. Seismic activity patterns, magnetic field changes, atmospheric disruption, and climate instability are all showing variations from historical norms. Thomas described this convergence of warning signs as significant for understanding planetary behavior, though his specific predictions about catastrophic outcomes lack scientific support. The correlation between current observations and Thomas's general descriptions of planetary instability has surprised some researchers who initially dismissed his work entirely. Expert opinions on catastrophic probability vary significantly depending on whether researchers accept conventional geological frameworks or consider alternative theories about rapid planetary change. Geophysicists who study magnetic field behavior acknowledge that current changes represent unprecedented observations in the modern instrumental record, though most maintain that catastrophic crustal displacement remains physically implausible. Mainstream geological consensus emphasizes that current changes operate through normal geological processes that unfold over extended timescales rather than catastrophic events. Independent research teams studying geological risk assessment have developed mathematical models for evaluating planetary stability using current magnetic field data, seismic patterns, and climate indicators. While these teams operate within conventional geological frameworks, their models show correlations between various risk factors that peak during periods of increased geological activity. The mathematical relationships between different planetary phenomena suggest that understanding these correlations could provide insights into geological behavior, even without accepting catastrophic displacement theories. Warning sign patterns observed throughout 2025 show some correspondence to sequences Thomas described, though these patterns operate through conventional geological processes rather than precursors to catastrophic events. Magnetic anomalies have accelerated, seismic activity has shown regional variations, atmospheric patterns have demonstrated unusual characteristics, and climate indicators have displayed instability. The sequence of these phenomena matches some aspects of Thomas's descriptions, though mainstream science interprets these changes as normal variations in Earth's dynamic systems. Current data acceleration suggests that geological processes are operating at rates that compress some traditional timescales for planetary change. Previous magnetic field transitions occurred over thousands of years, but current changes are happening at rates that represent significant departures from historical patterns. The compression of these timescales means that understanding geological behavior requires examining processes that operate faster than conventional geological wisdom previously acknowledged, though still within the bounds of normal planetary evolution. Multiple calculation methods indicate that geological systems are approaching periods of increased activity that warrant scientific attention. Magnetic field projections, seismic stress models, and climate instability calculations suggest that various planetary systems are experiencing changes that represent departures from stable baseline conditions. The synchronization of these different indicators suggests that Earth's geological systems are entering a period of increased activity that deserves careful monitoring through conventional scientific methods. Scientific institutions have expanded monitoring programs based on the need to better understand current geological activity patterns. Government agencies responsible for disaster preparedness have developed contingency plans for scenarios involving infrastructure challenges from space weather events and natural disasters. These preparations reflect standard emergency management protocols rather than preparation for catastrophic planetary events. The practical measures being implemented represent normal disaster preparedness rather than responses to imminent catastrophic threats. Current conditions may represent a period of increased geological activity that provides opportunities to better understand how Earth's systems behave during periods of change. Thomas's observations about planetary behavior, while containing elements that lack scientific support, have prompted researchers to examine correlations between different geological phenomena more carefully. Whether current changes represent normal geological variation or indicators of more significant transitions remains an active area of scientific investigation. The evidence suggests that understanding these planetary changes has become important for assessing how current conditions might affect human civilization. While catastrophic scenarios remain outside mainstream scientific consensus, the patterns emerging in geological data indicate that preparation for various types of natural disasters and infrastructure challenges represents prudent planning for an uncertain future. Survival and preparation strategies. Developing effective preparation strategies requires moving beyond theoretical discussions toward practical measures that address realistic scenarios rather than speculative catastrophic events. Individual preparation for natural disasters and infrastructure challenges should focus on established emergency preparedness protocols rather than planetary-scale survival scenarios. Standard disaster preparedness assumes that emergency services will restore normal conditions within reasonable timeframes, which represents the most likely outcome for natural disasters including severe space weather events, earthquakes, and extreme weather conditions. Geographic considerations for emergency preparedness involve understanding regional risks and developing location-specific preparation strategies. Areas prone to hurricanes require different preparation approaches than regions facing earthquake risks or severe winter weather. Coastal regions need evacuation plans for storm surge and flooding, while inland areas focus on power outages and supply chain disruptions. Mountain regions prepare for avalanches and isolation during severe weather, while desert areas plan for extreme heat and water scarcity. Understanding local hazards allows communities to develop targeted preparation strategies that address the most likely emergency scenarios they might face. Government emergency management programs provide frameworks for disaster preparedness that individuals and communities can build upon. FEMA guidelines establish baseline preparation recommendations including emergency supply kits, communication plans, and evacuation procedures. NOAA provides space weather alerts and preparedness guidance for geomagnetic storms that could affect power grids and satellite communications. State and local emergency management agencies develop region-specific plans that address local hazards and coordinate response efforts. These established programs represent tested approaches to disaster preparedness based on decades of emergency management experience. Emergency supply preparation should focus on maintaining resources for realistic disaster scenarios rather than long-term survival situations. Standard emergency kits include water storage for several days, non-perishable food supplies, battery-powered radios, flashlights, first aid supplies, and medications. Additional supplies for extended power outages include backup power sources, extra batteries, manual can openers, and warm clothing. Communication equipment including battery-powered or hand-crank radios provides access to emergency information when normal communication systems fail. These supplies address the most common needs during natural disasters and infrastructure disruptions. Technology protection during electromagnetic events involves following established guidelines for space weather preparedness rather than extensive hardening measures. NOAA recommendations include unplugging sensitive electronic devices during severe geomagnetic storms, maintaining backup power sources for essential equipment, and having alternative communication methods available. Simple protective measures like surge protectors and battery backup systems provide adequate protection for most space weather events. More extensive protection measures are typically unnecessary for civilian applications, as severe electromagnetic events remain relatively rare and usually affect specific geographic regions rather than global infrastructure. Community preparedness initiatives create networks of mutual support that enhance individual preparation efforts,